Welcome to qnawire.
We are first going to we need to describe the two periods of constant acceleration for the rocket. We know that for part one, it's in free fall, so the acceleration in the x direction is equaling 0. The acceleration in the y direction is simply equaling negative g. For the second period of constant acceleration, the engines are then turned on for the rocket, so the acceleration in the x direction would be equaling 3.0 g multiplied by cosine of 30 degrees. For the y direction, 3.0 g multiplied by sine of 30 degrees. We're going to let lowercase t be the total time since the rocket is dropped, and then we're going to let capital T be to the time the rocket falls before the engine starts for the rocket. Now, for part A, this would be the diagram. This would be the diagram of the, essentially, diagram of the the flight paths, we can say, of both the rocket and the airliner. For part B, we can say that then the x position of the plane, so we can say x position of the plane, would be equal to 236 meters per second multiplied by t. And then the x position of the rocket is going to be defined as 236 meters per second multiplied by t plus 1/2 of 3.00 times 9.8 meters per second squared times cosine of 30 degrees multiplied by t minus t quantity squared. And so we find that the graph of this equation essentially would be here. This would be where t, the time at the when the rocket engines start, and then you can see how it is a parabolic motion when you're plotting the position versus time. For part C, we know that then if we take y to be 0 to be the altitude of the airliner, we can say that then y of t would be equal to negative 1/2 g times t squared minus g times t multiplied by lowercase t times t, and this would be plus 1/2 times 3.00 9.80 meters per second squared multiplied by sine of 30 degrees, and this would be t minus t quantity squared. That would be for the rocket, of course. Now, the airline has a constant y. So for the airliner, we have a constant y position. So we can then say that the rocket is dropped at t equals 0, and the time t when the engine is turned on indicated by setting y equaling 0 for the rocket, and then we can solve t in terms of t. So essentially we're setting this entire equation equal to 0, and then we can use the quadratic formula for the variable x equaling t minus t. This is essentially going to be equal to 9.80 meters per second multiplied by t. This would be plus the square root of 9.80 meters per second squared times t quantity squared plus 4ac, so 4 times 7.35 meters per second squared multiplied by 4.9 times t squared divided all by 2 times a, or in this case 2 times 7.35 meters per second squared. And we then see that t is equaling 2.72 t. And we're going to use that the condition that we can say x of rocket, we can say here, x of rocket minus x of plane will equal 1,000 meters. And so then we find that here, 236 meters per second times t plus 12.7 meters per second squared times t minus t squared. This would be minus 236 meters per second times t. This would equal 1,000 meters. And I apologize for it being so cramped, but after plugging essentially this condition here into this equation here, we find that t is equaling 5.15 seconds. So this would be our answer for part C. And if we were to then graph this, this is what the graph would look like, y versus t, where this t here is again 5.15 seconds. That is the end of the solution. Thank you for watching.